A thermal scan moves silently across the glass skyline of Dubai. The digital readout climbs rapidly, revealing a surface temperature approaching 135 degrees Fahrenheit. Yet, separated by only a few centimeters of engineered glass, a luxury interior thermostat rests comfortably near 75 degrees. Two radically different thermal environments exist simultaneously, divided by a fragile, transparent barrier. The air outside does not need to reach 135 degrees Fahrenheit. The glass facing the sun can approach it. The cool room you stand in is not evidence that the heat does not exist. It is evidence that an invisible system is successfully removing it. To understand the machine behind that difference, first follow the sunlight. When a figure like 135 degrees Fahrenheit appears, it is easy to assume the worst. It sounds like an apocalyptic weather report that would render a city uninhabitable. But this number represents a different kind of extreme. It is an exterior glass surface temperature under strong solar exposure, not Dubai's ambient air. Surfaces absorb solar radiation differently than the air around them. You experience this physics every time you touch a sun-heated pavement or the bodywork of a parked car at noon. The ambient air might be 95 degrees, but the exposed metal will burn your skin. Under intense sunlight, peer-reviewed research has recorded exterior glass surfaces approaching nearly 57 degrees Celsius. That is the physical benchmark of direct solar exposure. It is not a constant condition across every facade, nor does every tower reach this extreme every day. But it proves the physical plausibility of an enormous temperature contrast pressing against the building envelope. If the glass is transparent, why does it become so intensely hot? Glass is often thought of as an empty opening that simply lets the view inside. In a climate like Dubai, it is actually an active checkpoint for energy. Imagine 100 units of raw solar energy striking a single pane of architectural glass on a clear afternoon. That concentrated energy immediately separates into three different paths. A portion reflects outward, bouncing off the surface and back into the sky. Another fraction transmits directly through the transparent barrier, spilling onto the interior floors as visible light and warmth. But a significant portion is absorbed directly by the glazing itself. The glass holds that energy, heating up as it acts like a thermal sponge. Some of that absorbed energy is then transferred inward through continuous radiation, convection, and conduction. Engineers use a precise metric called the solar heat gain coefficient to measure this exact process. It represents the total fraction of incident solar heat that ultimately enters the occupied interior through the fenestration system. Even with advanced architectural materials, that coefficient is rarely zero. Some thermal energy always crosses the boundary, creeping into the conditioned space. The term sounds highly academic, but its physical meaning is the foundation of modern building survival. Managing the heat transfer of one isolated pane of glass is a manageable engineering equation, but one pane is manageable. A skyline is multiplication. A modest fraction of heat flow seems insignificant when you examine a single window in a laboratory. But Dubai did not place one window in the desert. It built a sprawling skyline out of them. That small fraction of solar heat gain becomes a monumental physical force when multiplied by thousands of square meters of glazed area. It multiplies again during long periods of uninterrupted exposure to the afternoon sun. It multiplies across 80 repeated floors of a skyscraper. It multiplies across entire commercial districts stretching along the coastline. The transparency that gives the real estate its premium value is the exact property inviting this massive thermal load. The panoramic view creates the financial value of the room. Yet, the strongest afternoon sun often forces occupants to pull down heavy blinds, hiding the view they paid millions to acquire. The accumulating heat transforms the architecture from a transparent lookout into a defensive fortress. The thermal load builds relentlessly as the sun arcs across the sky, turning every western facade into a massive collector. The structure must process this continuous influx of solar radiation without ever showing a sign of strain to the occupants. Before the heat reaches the power grid, what does it do to the person sitting beside the glass? Comfort is rarely as simple as reading a digital number on a wall. Imagine standing in a premium corner office, surrounded by floor-to-ceiling windows overlooking the marina. The thermostat confirms the supply air is a perfectly chilled 75 degrees. You can feel the cold, conditioned air gently moving across the center of the room. Yet, as you stand near the glass, one side of your face begins to feel uncomfortably warm. The sunlight burning across the dark wood of your desk raises its surface temperature dramatically. The human body does not read the thermostat. It exchanges heat with everything around it through a process known as radiant asymmetry. Even if the air remains cool, the intense radiant heat from the sunlit window and the heated interior surfaces will make you sweat. The physical discomfort forces you to step back, retreating from the expensive perimeter. The blinds slowly descend, cutting off the harsh glare and shrinking your usable architectural space. The air conditioning is running at full capacity, but your body still registers the violent intrusion of the desert environment. This precise physical discomfort is exactly what modern facade engineering is designed to prevent. This is why engineers developed low emissivity coatings, insulated glazing, and sophisticated solar control. Dubai's architectural sector is highly aware of this radiant challenge. The city did not blindly erect transparent boxes in the desert without a rigorous, scientifically grounded defense strategy. Engineers deploy an impressive, multi-layered arsenal of technologies to protect the fragile interior environment. They use microscopic low-emissivity coatings, thinner than a single human hair, to reflect long-wave infrared radiation back outward. They install double and triple insulated glazing units, often filled with dense argon gas, to physically break the conductive path. They apply spectrally selective solar control layers that emit bright visible light while aggressively blocking invisible heat. Exterior shading fins, automated interior blinds, and strategic building orientation are carefully modeled in software long before construction ever begins. The Dubai Building Code and the comprehensive Al Safat Green Building Framework strictly regulate envelope performance across the entire emirate. These mandatory regulations demand vastly improved thermal transmittance values and enforce aggressive reductions in solar heat gain for all new developments. This invisible technological shield genuinely works. It limits the sudden thermal shock, physically protects the occupants, and keeps the interior climate incredibly stable despite the raging sun outside. For a moment, it feels as though modern human ingenuity has completely conquered the harsh realities of the desert environment. The high-performance glass appears to have permanently won the battle against the climate. But reducing heat is not the same as making heat disappear. Even the most advanced, high-performance glazing in the world does not create a zero-load building. The expensive layers of molecular protection merely slow the invasion of thermal energy. They do not stop it entirely. Heat still infiltrates the towering structure through multiple, unavoidable physical pathways. It arrives through the residual solar gain that inevitably manages to bypass the selective coatings. It transfers through slow, steady conduction, moving relentlessly through the aluminum framing of the massive envelope. It enters through the constant pressure of warm outdoor air, attempting to breach the perimeter seals of the facade. Inside the glass tower, the thermal load compounds even further. The human occupants themselves continuously radiate body heat into the tightly enclosed space. The bright overhead lighting, the glowing computer monitors, and the heavy elevator motors all generate friction. The necessary ventilation systems bring in fresh oxygen, but they also drag in heavy, humid, unconditioned outdoor air that must be processed. This is not the story of bad glass failing its intended purpose. It is the story of good glass facing an almost continuous, overwhelming source of raw energy. The physical reality is that the problem has merely been minimized, not eradicated. And the laws of thermodynamics demand a strict accounting for every single joule of energy. Every unit of unwanted heat that successfully enters the occupied space eventually has to be removed, moved, stored temporarily, or violently rejected elsewhere. The tower does not destroy that heat. It sends it somewhere else. The moment the heat breaches the architectural facade, it triggers a massive, hidden mechanical response. The process operates like an unbroken chain of custody, capturing the invasive energy and dragging it out of the human environment. Sunlight enters the room, and the interior air and surfaces immediately gain heat. A spinning fan pulls that warm air across a densely packed cooling coil. The thin metal fins of the coil absorb the heat from the air, instantly dropping the temperature of the room. But the heat has not vanished. It has simply been transferred into the chilled water rushing through the pipes inside the coil. That newly warmed water is then pumped away, traveling rapidly through dark pipe risers hidden inside the concrete core of the building. It flows downward, descending into a mechanical room filled with the heavy vibration of industrial machinery. Here, a massive chiller compressor uses electrical work to squeeze the refrigerant gas, extracting the heat from the returning water. Finally, the condenser unit violently rejects that collected heat, blowing it out into the hot outdoor environment. The air handling units, the spinning pump impellers, the pressure gauges, and the valve actuators never stop moving. They form the artificial lungs and circulation system of the structure. The transparent facade gives the building its iconic, weightless image. The mechanical room gives that image permission to exist. In Dubai, many buildings do not fight this battle alone. The sheer scale of the heat load in a dense, vertical metropolis requires a solution larger than a single mechanical room. Instead of outfitting every individual tower with its own massive, independent chillers, Dubai heavily utilizes district cooling. A central plant produces millions of gallons of chilled water in a highly controlled industrial environment. This water is distributed through a vast network of insulated pipes buried deep beneath the streets. It flows to dozens of buildings, absorbing their heat before returning to the central plant to be cooled again. It functions as a blue circulatory system spreading beneath the urban districts like hidden arteries. This centralized approach is often more efficient than maintaining thousands of independent cooling systems on crowded rooftops. It reduces duplicated equipment, lowers peak power surges, and frees up valuable architectural space. Yet, its sheer magnitude reveals a staggering truth about the city's design. At the end of 2024, Empower reported approximately 1.566 million refrigeration tons of connected capacity. They served more than 143,000 customers through this subterranean network. This monumental figure establishes the scale of the operation, not the isolated demand of one specific building. It demonstrates how many towers, malls, and residential blocks depend absolutely on the uninterrupted flow of chilled water. District cooling is not proof that Dubai has lost its battle with heat. It is proof that the battle has become too large for each building to fight alone. The city has externalized the thermal defense of its architecture. What powers a cooling network on that staggering scale? To move millions of gallons of water and compress tons of refrigerant, you need a tremendous amount of electrical force. The hidden cooling machine cannot function without an immense supply of raw power from the local grid. In 2025, Dubai's annual peak electricity demand reached an astonishing 11.39 gigawatts. This number represents the total citywide peak electrical demand required to keep the metropolis functioning during its most intense periods. It is not electricity consumed exclusively by air conditioning, skyscrapers, or district cooling plants alone. It includes the automated subways, the desalination plants, the server farms, and the industrial zones. But its scale establishes the extreme energy context within which the urban cooling system operates. When the desert sun is at its absolute highest, the substations hum with deep tension, and the transmission lines carry massive currents. Inside the control centers, operators carefully watch the digital demand curve rising sharply as the thermal load on the city increases. Every single ray of sunlight striking a glass facade adds a microscopic fraction to that rising curve. Millions of those fractions combine into gigawatts of necessary mechanical effort. In a climate-controlled city, comfort is not only a subjective feeling experienced inside a room. It appears on the power system as an undeniable, measurable demand. The glass skyline is inextricably wired to the electrical infrastructure, bound by a permanent contract of energy transfer. Yet presenting Dubai as unaware of this structural problem would be equally misleading. The narrative that modern engineers simply forgot about the sun is entirely false. Dubai regulates building performance rigorously, and the mitigation strategies currently deployed across the city are highly sophisticated. High-performance glazing works exactly as it was designed to work, deflecting immense amounts of radiation. District cooling can dramatically improve urban energy efficiency compared to relying on thousands of decentralized air conditioning units. Intelligent building management controls successfully reduce unnecessary cooling loads by tracking occupancy and adjusting airflow. Strategic architectural shading and better facade orientation demonstrably reduce the worst of the direct solar exposure. Engineers actively model, calculate, and manage solar heat gain long before the first concrete foundation is ever poured. The core problem is not an absence of brilliant technical solutions or a lack of engineering talent. The problem is the permanent, massive scale of the condition those solutions must constantly manage. This creates a second, more subtle illusion of architectural safety. More efficient glass, smarter sensors, and better chillers appear to easily solve the future of the city. But efficiency per square meter does not automatically guarantee lower total energy demand when the total conditioned floor area continues to aggressively expand. If a building is 20% more efficient, but the city builds 50 more of them, the systemic thermal load still increases. Technology can improve the physical performance of every single square meter. A city is measured by how many square meters it creates. This continuous architectural expansion leads directly to the genuine source of suspense hidden behind the skyline. The glass facade carefully controls the solar gain, passing the massive residual heat directly to the cooling equipment. The cooling equipment relies entirely on the steady chilled water flow, which depends heavily on the spinning pumps and digital controls. Those pumps require an uninterrupted electrical supply, which in turn demands constant, flawless maintenance and component replacement. This forms a perfect, unbreakable dependency chain. Consider a conditional scenario of a mechanical cooling interruption inside a representative glass building on a bright summer afternoon. If the mechanical system suddenly stops, the room does not instantly become a furnace. Initially, the heavily insulated room remains perfectly cool, protected by the thermal mass and the stored coolness of the interior surfaces. This delays the immediate effect, offering a brief, deceptive window of safety. But the solar radiation continues to pour from the sky without pause. The exterior glazing remains fully exposed to the elements, actively absorbing and transmitting thermal energy into the dark interior. Slowly, the perimeter zones nearest the glass become uncomfortably, noticeably warm. The automated blinds close tightly in a futile attempt to reject the heat that has already breached the envelope. Occupants retreat further from the facade, abandoning the premium views as the indoor air becomes heavy and the conditions progressively deteriorate. The utter silence of the missing machinery rapidly becomes the most terrifying sound in the room. The building is not an oven simply because the glass becomes hot. It becomes oven-like when the systems removing heat can no longer keep pace. The architectural comfort is entirely conditional. Dubai recognizes this dependency, and the city now faces three distinct, possible futures. The first future relies on building even more mechanical capacity. This means constructing larger cooling networks, generating greater electrical capacity, and designing higher efficiency chillers. It is a path of continued, brilliant compensation, using massive infrastructure to fight the heat after it strikes the glass. The second future requires a more defensive architectural envelope. This approach uses lower glazing ratios where appropriate, replacing entirely transparent walls with solid, insulated materials. It involves designing deeper external shading structures and creating facade geometry that physically responds to the orientation of the sun. It relies on spectrally selective glazing and adaptive facades that focus on passive thermal reduction long before mechanical removal is needed. The third future is the most difficult because it demands a new definition of luxury itself. In this future, luxury is defined by profound comfort, achieved with significantly lower energy demand. It means designing usable, framed views without the penalty of permanent, blinding glare. It embraces shaded depth, resilient interior conditions, and an architectural identity derived directly from the climate rather than a stubborn resistance to it. If a building needs a vast, industrial machine to defend its own skin for its entire life, is that machine supporting the architecture or completing it? The next generation of prestige buildings will have to answer that question. They will reveal whether the city chooses to display more glass or more intelligence. As evening arrives, the glass skyline reflects the sunset, as though the buildings are entirely weightless. Behind the reflection is an invisible network that makes the interior possible. The heavy blinds remain drawn. The chilled water pipes continue to sweat in the dark. The pumps continue their relentless rotation through the night. Inside the control rooms, displays monitor the slow transfer of heat from the concrete and steel. Glass does not defeat the sun. It slows the heat long enough for the machinery behind it to keep pace. And that is the hidden truth inside Dubai's cool, silent towers. Comfort in a glass building in the desert is not something the building owns. It is something the city must produce again, every second. This documentary is for educational and analytical purposes, examining building physics and thermal management systems based on currently available technical data. It does not predict the failure of specific structures, and conditions vary significantly depending on individual building design, maintenance, and evolving energy codes. What is your definition of architectural luxury in a changing climate? Share your thoughts in the comments below, and subscribe to Dubai Viral for more investigations into the hidden systems that keep our modern cities alive.